Welcome to the 16th class meeting of the Introduction to DSP. Even though this is a week for midterm exam, there will be homework. So we are covering around the halfway of the chapter 4, sampling of continuous time signals. But interestingly, the topic of today is sampling of discrete time signals. So the title is a little bit misleading. So remember, there are two types of sampling. One is sampling a continuous time signal to have a discrete time signal. Another one is what? Sampling of discrete time signal to have a discrete time signal. Got it? So be careful. It was very confusing to me 30 years ago. There is a kind of very complicated misnomer. So misnomer means, nom means name. So misnomer means 잘못된 명명법. But there are many misnomers in electrical engineering, probably not only electrical engineering, in every aspect of academia. But today we will see one of the most serious misnomer in electrical engineering. And that confuses students a lot. So be alert, not to be confused. Okay, here goes the review. So in the last class meeting, I spent a lot of time to expose you the idea of what? The sequence of functions and its convergence. There were around four different types of convergences. The first one was everywhere convergence. The second one was almost everywhere convergence. And third one was in the piece mean, especially when p equals 2, we had mean square convergence or convergence in the mean square sense. And the fourth one was convergence in measure. And we had interesting implication like this. So sometimes for your specific problem, you may need convergence in measure, but you don't need to prove this specific convergence criteria, but you may find proving almost everywhere may be easier. When it's easier, you may find some theorem written by mathematicians, and you find that your problem, so in your application, it's enough to show this, but you don't know how to prove it, but you find some math theorem, publish it in some math journal, and even appearing in your textbook, some of textbooks, and you find your problem, after probably some trimming or conversion, exactly fits to the theorem that shows almost everywhere convergence. Then use it, got it? And you just cite in textbook something, theorem, blah, 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 it's straightforward, blah, blah. Or sometimes you prove the mean square sense convergence. So you just handle expectation of the, not expectation, integration of the, so let me repeat here, especially for M2. So you have something like this, converges to 0 as M tends to infinity. And actually, this is what is used in the proof of what? Proof of sampling theorem. Got it? Especially Nyquist sampling theorem. So we have this theorem, blah, blah, blah conditions, and we have this one. So here is our original continuous time signal, and here is the sampled version with sampling rate 1 over capital T. And here goes the sync pulse, but need to be properly scaled so that it intersects at every integer. And you have shifting and square dt. And here goes the sum over, just a second. Something's confusing. Let me use n here. Indexing is always confusing. So let me use k from negative n to n, and k. And then what do you have? You have some sequence of non-negative real numbers. And the nth term, so you fix n, you fix the upper limit and lower limit of this summation. So you have only a real number that can vary by n, right? By changing n. So you have a sequence of real numbers, and that converges to 0. And this convergence in the mean square sense is appearing in the Nyquist's original sampling, not original, Nyquist sampling theorem. Got it? So here, what do we have? We need x of t need to be what? Finite energy, strictly band-limited signal, and its highest frequency content, the highest frequency, must be less than half of the sampling rate 1 over capital T. Then you have this convergence in the mean square sense. So that is the entire story. By the way, this sync pulse used in the perfect reconstruction, maybe change it, because sync pulse is not a causal signal. It has infinite support. So in a practical signal processor, you may replace this one with some other interpolation functions, such as a rectangular pulse. In that case, you call the interpolator as a zero order hold. And if you replace it with a triangular pulse with width 2 capital T, so negative T, positive capital T, and height is 1, then it's virtually same as you linearly interpolate the sampled points. In that case, it is called first order hold, because the straight line is kind of T to the 1, something like that. Got it? Of course, ideal interpolation is done by sync interpolation function or interpolation waveform. And then we quickly moved to, and very quickly covered, and most of the burdens are left to you, to the section 4.4 and 4.5, where DT processing of CT signals and CT processing of DT signals are covered. And I gave you just some examples. Even though the examples does not fit exactly to this CT processing of DT signals, but the idea of, for example, surface acoustic wave filters used in radio communications or radio applications such as radar system, it's very similar to convert the radio wave to do some discrete time processing. Got it? So you exploit the fact that radio wave is much faster than the acoustic wave, or vice versa. Acoustic wave is much slower. So using a very small form factor, so-called form factor, you can introduce very large delay. If it could be done using a radio cable, radio frequency cable, it could be 100 meters long. But if you convert the radio signal to an acoustic signal, then you can achieve large delay in the order of some milliseconds very easily. Got it? So that is the idea. Anyway, so here, as an example, we studied some non-harmonically related rate sampling. So originally, you sample the signal at every capital T. But you changed your mind and you want square root 2 times T or square 3 times T, then what can you do? In that case, one simple way is to convert it back to a continuous time signal and sample again. Today's topic is a little bit different. And this is more interesting. And here, all the samplings are related to the conversion into harmonically related rate, which means that if you sample the continuous time signal to obtain a discrete time signal, then probably your x1 is defined as something like this. Now, you want is it M over L? I'm not sure. Something like this. Got it? Just a second. Yeah. I will. I'm almost sure this is what appears in the textbook. So, so given a continuous time signal x, probably you have sampled the signal already. Now you changed your mind. You want this rational multiple of the sampling period as a new sampling rate. Then what can you do? Do you need to convert the signal back to a continuous time signal and resample? Your answer is what? No. You can combine what we are going to learn today, two things, downsampling and upsampling. Actually, you can achieve this. That is the topic of here, and also this one. Got it? So this is a big picture of upcoming class meetings and today's class meeting. So here goes the first page of section 4.6. So the title is Changing the Sampling Rate Using Discrete Time Processing. And here we have two things to learn. First one is downsampling, and second one is upsampling. So here we've covered the sampling of a continuous time signal already in the previous sections, right? To obtain a discrete time signal. Different from the previous ones, this section 4.6 is about this. Got it? Sampling of a discrete time signal to have a discrete time signal. But there are two types of sampling of discrete time signals. Actually, two names. And one is upsampling, and the other is downsampling, and the other is upsampling. However, we already have learned in the previous section interpolation of a CT signal, right? D2C converter. That is interpolation, right? And if we name it correctly, it was the interpolation of a continuous time. Just a second. Sorry, interpolation of discrete time signal. Sorry about that. Discrete time signal to obtain a continuous time signal, right? But here we learn something strange. Interpolation of discrete time signal to obtain a discrete time signal. And that is actually related to upsampling. So it's kind of, how to say that in Korean, 족보가 꼬인. So we are very confused, and it's not your fault. It's very, very confusing. But anyway, as the first 15 minutes of the class meeting, remember this one. There are two things, upsampling and downsampling. Got it? And also, there are similar names, decimation and interpolation. So you remember these two pair, this one pair, up-down sampling, and remember these two, decimation and interpolation. And how they are related, one good thing is that, actually, this was my way of memorizing because it's so confusing. So it's like, hey, it starts with D and it starts with D. They are similar. It's kind of elementary school students' way of memorize something. And here goes P, and here goes the P. So downsampling is related to decimation, and upsampling is related to interpolation. That's the way to remember. Got it? So these two are related in the sense that they are similar. Actually, downsampling is a special kind of decimation. You will see. And upsampling is a special kind of discrete time interpolation, DT interpolation to obtain DT signal. So DT interpolation to obtain a DT signal. Here, DT signal interpolation to obtain a CT signal. That was covered in the previous sections. Got it? The first thing is very simple. Suppose you already sampled the continuous time signal to obtain a discrete time signal like this with sampling rate 1 over capital T. Now you changed your mind. So you want a new signal, x1, that has different sampling rate, 1 over capital T sub 1. And T is different from T sub 1, but they are harmonically related. What does that mean? If the sampling periods are harmonically related or equivalently sampling rates are harmonically related, their ratio is a rational number. In that case, we call they are harmonically related. Got it? Not just the integer multiple. Probably some of you have some knowledge about the harmony or harmonics in music composition. Then you know that some do, mi, sol, they are not exactly, in do, mi, sol case, they are exactly integer multiple. Okay, so when you have a do, mi, sol, then you have integer multiple of frequency mi and sol, but sometimes you have something different. They are harmonically related and sounds very beautiful. Got it? And usually they have this relation. Now, when do we need change in the sampling rate? For example, in the two-dimensional signal such as image, we want to reduce the size. And what do? We may want to resample. And sometimes when we increase the video quality or audio quality, we need that. By the way, there are some criminals who wants to make up the proof to be submitted to the court. And they combine some voice recording of me, for example, talking about some history and saying, for example, I admire, I'm not, but I might say that and some other things, and some North Koreans admire Kim Jong-il, something like that, and they cut and mix with two files recorded in different day. In that case, sometimes the first recording is sampled at 44.1 kilohertz, but sometimes it is recorded at 20 kilohertz. When they combine, these criminals usually make mistakes. They didn't take the DSP course. So they just simply convert, and the National Criminal Investigators Office, 국과수, they easily find by just looking at the made up file that, hey, something's wrong. And also another thing is that usually the different equipments has different noise. So they try to see the power spectrum of the background noise. And when they combine two different things, suddenly noise level goes up and down when they cut and put. So it's a kind of very simple thing. Anyway, so here, the authors of the textbook says that the direct approach is to convert back to continuous time signal and resample. And sometimes that could be the only way. However, when we have harmonically related rates, then we can do it much easier, much easily. Got it? So here goes the first thing. So I said we have two discrete time sampling. So we have DT signal in, and there are two types of sampling, upsampling and downsampling, or downsampling and upsampling. Got it? The first topic is downsampling because it's easier to understand in the time domain. However, it's difficult in frequency domain. Got it? So let's see what is downsampling in the time domain and what's the DTFT before and after downsampling. So as I already told you, this D is related to decimation, right? So you will see decimation in this subsection too. Okay, here goes the standard notation, 표기법, and see here is a box, block, and you have a down arrow and M. It is read as what? Down by M, right? Got it? Very simple. Down by M. But it's, if you decompress the compressed version, downsampling by a factor of capital M. That is the way you call or you read this box. So it's like you have a discrete time signal X of N, you have a downsampler by a factor of capital M to obtain a DT signal X of D of N. Got it? I really hate this one. Yeah, why authors use this one? Okay, let me use different one. So let me use M. Got it? And you will see why I love to use M instead of N. Okay, so here. Yeah, sometimes the OneNote does not work. Okay. Uh-oh, again. Just a second. Okay, got it? The reason is that here, suppose you have a clock, then at 1 unit clocking or ticking, suppose this signal changes. Then what about this one? If you define XD of M in this way, you will have one output at every capital M ticking, right? So I want to use different time indices. So suppose you have a real world clock T, and here is your N. Then this is your M when capital M equals 2. Got it? So I want to use different time index. Otherwise, it's very confusing. Got it? So if you see this way, then it's very easy to understand. For example, suppose you had the continuous time signal X this way, then what happens? In your original X, you sample here and there, and there, to obtain a discrete time signal X. But now, by defining this way, actually you discard m minus 1 samples. In this case, 1 sample when capital M equals 2, you see? So you just discard that one to have this one, and this one, and this one, dot, dot, dot. Got it? So this is downsampling. Very simple, right? So downsampling by capital M means you find the reference, the downsampling time. By the way, sometimes you may have some offset here, and again, we kind of ignore that one. But it's very important, actually. That makes the difference. As I told you in the continuous time signal sampling, there were 2 parameters. What was that? The first one is the most important thing, that is the sampling period. What was the other one that is often ignored? Sampling offset. Similar here, you may have, if you have defined this way, what does that mean? X of 0 is always included here, right? So it's like you have some time origin 0, and from that, you discard capital M minus 1 and keep next one. Discard capital M minus 1 and keep 1. But actually, you can shift by 2 and then may discard M minus 2, sample, keep, and discard M minus 2. So even here in analogous of the continuous time sampling, you may introduce an offset. So be careful. Ready? Anyway, so in the time domain, it's very simple. You just remove capital M minus 1 samples. Sometimes this operation is called compression, or the downsampler is called compressor. Now, here goes the question. Suppose your original discrete time signal was a sampled version of a continuous time signal. Now, you just downsample it. Then the question is obviously, is perfect reconstruction possible? Assuming the original signal x of n was perfectly recover the original signal. And your answer is what? Your answer is, in general, no. And because here, it's like you sample at every 2 capital T, and that may not be faster or equal to the Nyquist rate of the original signal. Even if the original sampling with capital T was okay for Nyquist sampling theory. Got it? So here, this is the original sampling rate. And by doing downsampling by a factor of capital M, actually you are doing low rate sampling now. And if your sampling rate decreases, aliasing may occur, depending on whether this new sampling rate, where it is, new sampling rate, omega sub n, no, not omega sub n, omega s divided by m, where it is, omega sub s divided by m, this is new sampling rate, may be still satisfying the Nyquist condition or not. Depending on whether it satisfies or not, perfect reconstruction is possible, or sometimes aliasing occurs and you cannot perfectly recover the signal if you don't have additional information for perfect reconstruction. Now, this part is very, very confusing. And the simplest way is to think in this way. Everybody, be careful. Downsampling is not always related to resampling a continuous time signal. However, to understand what's going on in the frequency domain, you may have better think in that way. Okay, let me repeat. Downsampling is what? A DT signal in, DT signal out processing operation. Just that. The input signal needs not to be a sample diversion of a continuous time signal. However, to understand what's going on in this downsampler or compressor, you'd better think in that way. There is an original continuous time signal and you sampled already, and now you add, serially connect a downsampler. And what would be the eventual frequency domain representation? So think in this way. So you have X, and here is the C2D with T, and you have X of N, and here is the downsampling by the factor of M, and you have, let me see, XD of M defined as XM capital M for all M. Ready? Now, let me ask you then, what was the relation between this DTFT of the sampled signal and the original continuous time signal? Anybody? We derived this one by using some fictitious system, two-stage representation of C2D. First, you had what? The impulse train generator and multiplier, and then you have continuous time modulated impulse signal, and then you had strange block that does not exist in the real world, but mathematically exists. We had the modulated impulse to discrete time system. But what was that? Very simple. It's like sampling rate in radiant frequency times folded spectrum of what? Of the original continuous time signal. So here you have J, but you need to scale. So T omega minus 2 pi. Let me use LT. Am I right? 2 pi L, sorry. And here goes the L's. Am I right? Just a second. Yeah, I believe so. Yeah. So this was the relation. Now, I'm asking you, what is the relation between X DTFT of this output of the downsampler and the input of the downsampler? And you may, of course, directly derive the result from this relation in the time domain. But as I told you, I advise not to do that. So just view it as what? As a big C2D converter with now the sampling rate changed to this one. Got it? Right? Sorry, M capital T. Confusing. Right? So for the first thing is very simple. You just copy this line by replacing every capital T with capital T sub D. So now what do? You replace this one. So here goes the result. So here still you see that this signal, sum of infinite terms, by shifting the first one, capital X of j omega divided by capital MT by 2 pi integer multiples of 2 pi gives you a periodic signal with period 2 pi. Got it? So now let's compare these two, this one and that one, and let's plot it in the frequency omega domain. And let me show you this one first, because this is more easily understandable. So here, let me see, what is XC? Okay, XC, just a second. So let me put C here, C and C and C and C. Ready? So here goes the CTFT of the original continuous time signal. If there was an original CT signal. Okay. As I told you, in downsampling, actually you have only 2 frequency domain DTFTs, but we assume that there was some continuous time signal, and that is given here. And from here to here, with sampling rate 1 over capital T, what happens? You have periodic signal with period 2 pi, and what happens to this one? This one becomes here some omega sub n, that is what? That is capital omega sub n times capital T. Got it? So suppose this was 5 kilohertz, and you had the sampling rate 20 kilohertz. Then what happens? This becomes what? 2 pi times 25 divided by 24. Yeah, something like this. Got it? And now, what happens? You choose capital M equals 3. So you now have down by 3. And one simple way is this one. Now this 5 kilohertz is not sampled at 20 kilohertz. It's sampled now at 20 kilohertz by 3. Then what happens? You have this omega sub n translated to a bigger number. So it's like you just extend this one 3 times and then repeat. So you have this one kind of stretch it. Got it? And that one stretch it, and that one stretched by 3. But be careful, the first one is still centered at 0. Second one is still centered at 2 pi. And the third one is still centered at negative 2 pi. You just stretch by m times. Got it? And then you add up. Got it? That's the way to remember. And what will happen? Aliasing occurred in this case. What if we have a very beautiful case? So still downsampling by a factor of m does not give you overlapping in the spectrum domain. Then, where it is? Yeah. So let's compare these two. Just a second. Yeah, I believe so. Ready? So you sampled to obtain the DTFT of the x of n, and then you downsample x of n by 2. Then what did I tell you? You stretch this one twice, 2 times, so you have this one. And you stretch this one, then to obtain that one. And you stretch this one to obtain that one. Got it? Yeah, that's the way. So, as you've seen, aliasing may occur. And sometimes aliasing is okay. Anyway, you downsampled, right? Consider the Cosby stock market example. The packets comes very quickly to your computer. And your computer cannot process very fast. So you just save the updated numbers at every 5 seconds. And now you purchase a new one and found that your new computer can save, for example, your new old computer is down. Some virus has come, and suddenly you grab your old notebook and found that you have to save at every 10 seconds. Then just you drop equivalently the other sample of the previous recording, right? So in that case, just downsampling is okay. However, suppose you have a very high quality audio. So you have, for example, in this computer, you have a continuous time to discrete time A to D converter that samples my voice, for example, 100 kilohertz. So that not only my voice, because my voice does not span very large, but some strange ultrasound signal we cannot hear is still recorded. And if it is played later, some bats that can, or your dogs who can listen to higher frequency than human may enjoy some chopping signal of some grasshopper, something like that, which we cannot hear. But you suddenly have found that that's a waste of your hard disk. So you have decided to downsample. What will happen? What will happen if you recorded ultrasound signals which cannot be anyway our speaker, usually the loud speakers we purchase installed in this room, does not cover that high frequency. That they cover only the audible range of the average human being, usually. So anyway, even though your original fast rate sampled signal contained that's flipping or grasshoppers strange high frequency noise, anyway, we couldn't hear. Now, you downsample by 2 to convert it to, or let's say that before it was 88.2 kilohertz. Now you downsample by a factor of 2 to have 44.1 standard CD quality sampling rate. Suddenly, you just downsample and play, you hear something strange. Some grasshopper signal frequency translated as you see here. See that? Suppose how do you say that? It's very complicated yet. Okay, so let me be careful. Okay, anyway, that part I will explain it later, not right now, because otherwise I will not have enough time to tell you about upsampling. So anyway, so what they do is that they usually just, okay, then let me put a filter that is called anti-alias or anti-aliasing filter. So what you do is that before you downsample, you put low pass filter so that no aliasing will occur. So here, before you downsample, what you do is that you put a filter, pre-filter, to avoid aliasing. So here, you filter this signal to obtain that one, and then what happens? This part expands to this one, and that part expands to this part, and this one expands to this one. And you see that no aliasing occurred, even though you already lost some information here in the high frequency. And these high frequency components were what? What you could not hear because of our limitation of our audible system. Got it? But here, be careful. See that? What may happen? Right? So this part could appear here. So it's not like this one. So you had my, for example, recording, speaking this fast. And now you decimate, downsample by 2 without pre-filtering and play it. Then it could be like this, slow twice. But you also hear some strange noise, usually high frequency, clicking noise, something like that, without having the pre-filter. Got it? So usually, if it is an audio signal, you downsample, it just becomes slower, plus some alias. Got it? Please remember this. Anyway, by the way, now here comes decimator. As I told you, downsampling has D and decimation has D in common, and they are related. And decimation is what? This two-filter processing. Got it? So if you have only this one, it's downsampling. But if you have pre-filter, it is called decimation. By the way, what is decimation? Dec means 1/10 or 10 times, right? As you know, December is actually the 10th month, but Augustus, just wanted to put his stepfather's name, Julius Caesar, July, and his name, August, as 2 months. So everything shifted by 2, right? You know that. You know the story, right? So octopus has 8 legs, but October is 10th month something. And I really hated Augustus when I realized that one, because I had the trouble when I was a first-year middle school student. Anyway, so in Roman Empire, they had a strange punishment method. Actually, it is to make their soldiers fight very vigorously. So it's like this. If some hundreds or thousands of soldiers lose their battle, what happens is like this. For example, we have national identification number, and suppose the last digit of the first section, which is the last digit of our birthday, and it's naturally divided by 10 and the remainder, right? So what happens in Roman Empire is that, so we lost the battle, and the general chooses one lottery ticket, and it says 5, and your birthday is, for example, January 25, then you are executed. And all your friends in the your friends having the dates 10, 5, 10, 15, 20, 25, 30, they are all killed. So you don't know before you lose the battle. So you have to fight very vigorously. Anyway, so it's like 1/10 of the soldiers are punished. That is decimation in Roman Empire. So it's like reducing something. So the traditionally decimation, the European people perceives it to reduce some size. And our downsampling and its general version of decimation does what? Reduce the number of samples if it is sampled from a continuous time signal. Before you had 100 mega samples. Now, after you decimate or downsample by a factor of 2, then you have half the number of samples, right? So it is called decimation. And here goes the way to rewrite decimation, decimator, or downsampler. Actually, decimator, because we assume there is a filter. And let me show you the result first, because this block really confused me 30 years ago, 1995, the spring semester. My last semester in my undergraduate study, I was taking the introduction to DSP from a professor. And so the story is like this. So we have what? We have actually, we want this. We want to implement this one. And you may say that, what's the big deal? Just implement a digital filter that closely approximate the ideal low-pass filter with cutoff frequency, radian frequency pi over capital M. So after you filter, you just downsample by a factor of M, done. So when I first saw this, what's going on? What was professor talking about? Because it was too simple. But I advise you never do that. Okay, whenever you have alternative, perfectly equivalent representation, just say, hey, I know this well. I don't need this. Never say that. Okay, because that equivalent mathematical expression may give you to have much better real-world system when you want to implement it. Got it? Anyway, so this one is now what? Converted to, by the way, here, be careful. Here is x of n, x tilde of n. And if I keep my notation, we have xd of m, right? So this is kind of reduced rate signal. Got it? Or compressed signal. Now, here you have. See that? The textbook ignored this part, but here goes original x of n. That corresponds to this one. And now, here goes serial to parallel by a factor of m. So what you do is like this. Here, you have a scalar valued length 1 signal. Now at the output, you have scalar valued capital M signals. So for example, here you have x0, x1, x2, x3, x m minus 1, and x capital M, dot, dot, dot. What you do is that you group these capital M samples or terms of the sequence, and then put each one here, here, and here. Got it? And in the next round, what happens? You take x of capital M and put it here. So this serial to parallel converter actually already has reduced rate at the output. So it's like you have 1, 2, 3, 4, dot, 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 and capital M, and then you have one vector valued signal at the output. Got it? And then here you have m plus 1, m plus 2, 2m. Then you have another length capital M vector valued signal. Got it? And each one is filtered by a DT-LTI system with impulse response very strange. So suppose your original low-pass filter's impulse response is capital H, then you have some strange impulse response. So let's say, let me use. So here, this must be M then. Really hate. Yeah. And here you also have M. Ready? So the first filter, let's say its impulse response H sub 1 of M is defined this way. H sub 0. H sub 1 of M defined that way, and H sub capital M minus 1 of M is defined this way. Ready? So they share the same impulse response of the original anti-alias or anti-aliasing filter. It could be ideal or approximately ideal low-pass filter. Anyway, if you have H of N, then you construct capital M impulse responses by slightly shifting the samples. So it's like, suppose this is the index N, and you have impulse response like this, H of N. Then to make everything simple, let's assume M equals 2. Then what about this one? You take this one, and this one, and that one to have what? H0 of M. 0, 1, 2, 3, right? And what about this one? So at M equals 0, you have H of 1. So this one comes here. And that one comes here. And this one comes here to construct H sub 1 of M. Got it? So be careful. By the way, this is composed of capital M filters, and usually this entire thing is called a filter bank or a bank of filters. Not 은행, just the collection, right? A bank of filters, filter bank. So each slowly sampled version with what? Actually, this serves as what? This serves as offset, right? Got it? These serve as offsets, different offsets. So as I told you, in sampling or over continuous time signal and downsampling over discrete time signal, offset is actually important. And here appears in the alternative implementation method. So you have a continuous time signal, and what you do is that you sample with 0 offset, the original signal. And you sample with offset 1, you sample with offset 2. So here, from here to there, there is no information loss because they are same signals rearranged, right? This is a discrete time signal, scalar valued. This is a discrete time signal, vector valued, and with slow rate, with different offset. And interestingly, impulse response is also constructed by sampling the original impulse response with different offsets. Got it? Got it? And then you have capital M signals, and this part is very important. You add up. This is sometimes called combining or combiner. So the signals are already low rate signals. The output is a low rate signal. Got it? So overall, you have a high rate scalar valued signal, and you have a low rate scalar valued signal at the output of the decimator. And this part serves as the anti-aliasing filter or pre-filter before the downsampling. Got it? Yeah, let me. And by the way, this part, you do it yourself. It's not that difficult, but will appear in your homework problems. Okay. Now here goes upsampling, and we have, unfortunately, around 10 minutes. So let me emphasize the difference between the downsampling we've just learned and the upsampling. Anyway, their names are different, right? And upsampling is like this. In downsampling, you have kind of compressed the signal. Now in upsampling, you kind of decompress, but not decompress. Increase the number of samples, given the same samples. And suppose you have 100 values. Now you want to expand it to 1,000 samples. What do you do? The simplest way is to repeat each sample 10 times, right? But that is not upsampling. Actually, it confused me a lot because to me, this was so intuitive. Intuition. 직관적인. So I assumed, hey, upsampling would be repeating M times. So you insert capital M minus 1, same values between two different values. So if you have 0th sample, you repeat that at M minus M times, so you have virtually inserted M minus 1, same value. And then you have the first sample, and then you repeat that M minus 1, something like that. I thought that way. But let me tell you, it is not upsampling. Upsampling is to insert zeros, zero-valued samples. Got it? So please remember this one if you don't want to be confused. Got it? And what is this one? Actually, we are going to define this one as upsampling. And as I told you, downsampling is generalized as decimation. And upsampling is also generalized to discrete time interpolation. And actually, this is an interpolated version of the original signal with interpolation function, a rectangular function. Got it? So this is more fundamental in the sense that it's simple. You just insert capital, L. They use different one. L minus 1. And here goes the block diagram. This is what probably I wrote here in the next page. Yeah. As you see, up by L, or upsampling by a factor of L. Okay. We usually in downsampling we use capital M, and in upsampling we use capital L. Okay. And this is called expander. And before in downsampling we had compressor. Okay. Compress, expand. So compressor and expander. Got it? And even though the author says this is upsampling procedure, but actually it is not. Okay? This is upsampling procedure. And if you combine upsampling followed by some filter, it is called interpolation. Of course, there are many people who just say interpolation, discrete time interpolation is upsampling, but some people like me who is very picky in selecting and defining their terms don't agree. Okay, so as I told you, this simple block with up-down arrow is called upsampler or downsampler. And if downsampler is preceded by a cutoff anti-aliasing filter, the procedure is called decimation. If your downsampler is followed by some interpolation filter, it is called interpolation. Got it? So please remember this one. Otherwise, you will get confused up until you retire as an electrical engineer. Anyway, so in the time domain, it's very, very simple. So here, new signal. I really hate really this. Yeah, I really hate. Let me use L here. Got it? Then, yeah. L. Okay. So here, the rate is increased already. Got it? So this is low rate signal, and this is high rate signals. And as you see that this signal, after upsampler, has a lot of zeros. Got it? But still have the original signal. Got it? And in the frequency domain, this is very simple. You just plug in this rewriting of the signal. So see that here, very interesting thing is that your zero inserted signal can be actually rewritten this way as a convolution of delta function with some, actually not convolution, with some strange L times K, right? Usually it's a single. Anyway, this is actually serves as a interpolation, serves as an interpolation function. But since this is a delta function, it does not interpolate actually. But if you replace this one, delta, as some filter P or H, then you really have an interpolation. For example, if this delta function is replaced by all 1 and 0, 0, 0, 0, 1, 1, 1, capital L times 1 and 0, 0, 0, that is same as our intuitive upsampling, repeating capital L times. Got it? And after you have this equivalent relation, this is very important actually. In digital signal processing, sometimes this looks very easy to understand, but you have to be able to convert this way. Got it? Without having 4 and something elsewhere, don't do that, okay? Just put them together by introducing here, for example, an direct delta interpolation function. And then your upsampled signals, DTFT, can be very easily obtained. Original signal compressed in the frequency domain. You do in expansion in time domain, and you do the compression in the frequency domain. So here is your signal. Forget about this. Forget about this. Okay. Now, suppose you have this DTFT of the original signal. Now you upsample L times by a factor of L, and here L equals 2. Then what happens? You just keep this one, and let's copy and print this one in the rubber plate, and you compress the rubber plate twice, and then you put the markup like this. So this one now becomes, this one now becomes pi when L equals 2. Got it? So you still have a periodic signal with period 2 pi. Now what will happen if you do this? So suppose you have recorded a voice and then you put a lot of zeros. And you may say that, okay, sorry, just a second. Is it? Yeah, just a second, just a second. Yeah, I explained incorrectly. Okay. When you downsample, actually, it comes very fast. Okay. So in the last example, in the downsampling, if I recorded the signal and if I downsample and play it at the same rate, then because this is the correct tempo, but now it's compressed and speak very fast. So I'm sorry about the confusion. So here, now you have inserted zeros. So intuitively, if you play it with the same interpolation rate, conversion rate, probably it will slow down my voice, but actually it does not hear that way. Actually, it's slow but very high frequency. Why? Because you have these things. Now this is now 2 pi. So before, for example, you have only this part very important, but you have that part gives you very high frequency signal. So what do you need? You need filter, interpolation filter. In this case, that removes this part to keep this one. It is time to wrap up. And that one. And that one. So this is the function of the filter following the upsampler. Okay. Anyway, so we've just covered the interpolation, upsampling, decimation, and downsampling. So let me switch these two. So we learned about downsampling first. And if downsampling is preceded by a filter, that is called decimation, DD, right? And now you have upsampling that inserts zeros, but it may be followed by a filter. In that case, it is called interpolation. If the filter is identity filter, which means it does nothing, then it's upsampling, it's downsampling. Got it? Anyway, so the textbook also says upsampling is an interpolation. Upsampling is an interpolation, a subset. Got it? Here goes the idea of linear interpolation in the discrete time domain. And you can understand it in the frequency domain. That's not that difficult. And here again goes the efficient way of implementing upsampler. And you find it similarly. So it's almost parallel. So you find which one is which one. And here, you will have L here. Got it? Okay, so I will assume that we have covered up to here. Got it? Okay, that's all for today.